You have probably heard of this thing called climate change.
Climate change.
One of the biggest drivers behind climate change is CO2 emissions because carbon dioxide acts as a blanket for our Earth and traps the sun rays in and then causes the planet to heat up. This is quite bad and can lead to some terrible places. But if we want to solve it, we obviously need to reduce CO2 emissions. And one of the biggest sectors that causes these CO2 emissions is energy. So this accounts for about 73.2% of all CO2 emissions. This is pretty obvious seeing as we need energy for almost every aspect of our lives. And if we want to, we get to about 15 billion tons of CO2 that were emitted in 2019 for electricity and heat alone. Seeing how much of a role energy plays in our CO2 emissions, you'd think that we want to optimize it. And I'm sure we are working on it. But would you believe me if I told you that we are wasting about 67% of our energy? Sad, but it's true. We are losing over half of our energy due to heat. So this is probably something that we want to figure out how to fix. Obviously, the ideal thing to do would be to capture that heat and convert it back into electricity. Unfortunately, due to the laws of thermodynamics and physics, converting between forms of energy is pretty bad for efficiency. We're not going to be able to get 100% of that heat energy back. However, there are a few ways to do it that allow us to capture some of it. And perhaps the most common one is the steam turbine. And basically, this uses the heat to heat water, which will then rise as steam and turn the turbine. It's got an efficiency of about 30 to 40%, so not too bad. The other way, and one that I personally find a bit more interesting, probably just because I hadn't heard of it before, is thermoelectric devices, which are powered by something called the Seebeck effect. Okay, so basically the Seebeck effect is just using a material to convert heat directly into electricity. And another way to think about it is to think about something called the Seebeck coefficient, which is basically a measure of how good of a Seebeck effect a material can generate. But basically, it just says that if you heat up one side of a material, you'll be able to generate current. And how it works is that when you heat something up, the particles inside it start to move faster. That is basically what heat is. But if you heat up only one side, then the particles are going to start moving faster in there. And there's not going to be as much room for them because they're going to bump into each other and act kind of like bumper cars. So the particles, and specifically the electrons, are going to flow to the colder side of the material because there's more space for them over there. And because we have a flow of electrons, we have just generated current, which can be harnessed if we combine two materials, one with a higher Seebeck coefficient and one with a lower Seebeck coefficient, we can create a full circuit. And from there, we can harness that current as electricity. And so basically, the one with the higher voltage generated is going to overpower the one with the smaller voltage generated, and it's just going to flow in a complete circuit. So there are a couple factors that affect a material's ability to be able to use in thermoelectric devices. The first one is quite obviously the Seebeck coefficient. A higher Seebeck coefficient leads to better thermoelectric performance. The second one is electrical conductivity. We need a material that has high electrical conductivity because we want the electrons to flow very smoothly through the material with little resistance, because resistance would mean that we had lost energy. And then the third property we need is thermal insulation. So if we have one side of the material that's hot and the other side that's cold, and this material has good thermal insulation, then it's not going to equalize that temperature difference, which is good because the bigger the temperature difference, the bigger the voltage generated. If a material has really good thermal conductivity, it's going to neutralize that temperature difference really quickly, and so we won't be able to generate electricity for very long. And then the final property that we need is a low charge carrier concentration. So in short, this basically is connected to the Seebeck coefficient, and lower charge carrier concentration means higher Seebeck coefficient. Even though I realized that their efficiency is not that great, I was still super interested in these devices and I wanted to make my own. So it was actually not that complicated and I didn't even need that many materials. I just needed a thermoelectric generator, which you can find on Amazon, and then double-sided thermally conductive tape, a voltmeter, tea lights and a lighter, water, ice, and salt, because if you add salt to it, it makes it extra cold. And then I needed a metal tin, and then twist on wire connectors. Okay, so once I got all my materials, the first thing I did was attach the thermoelectric devices to the metal tin. It's pretty straightforward, But the only thing that you need to remember is to put the side with the words on it facing down, because that is going to be the side that is exposed to the cold temperature. And in my case, I was putting the cold water inside the tin. And then after that, the second thing I did was attach all of the thermoelectric devices in series. So basically, I trimmed the wires a little bit, and then I twisted a orange wire connector on top. And then I also taped these up on the side to keep them out of the way of the flames. And then I left the ones on the end a bit longer because I wanted those ones to be able to hook up to the voltmeter. So after that, I made a stand for my metal tin, and I took the simplest option and I just used a bunch of wooden boards. So I just stacked them up until they were the right height, but you could probably do something similar, or you could do something with metal or whatever you can find around your house. But do be careful though, because there is going to be fire near those. So I just put tinfoil on top of my boards to kind of protect them from that. And then after that, it was basically time to run the experiment. So I just put my metal tin on top of the stands with the thermoelectric devices attached, and then I filled up the tin with water, salt, and ice, allowing it to get cold. And I also added some tea lights underneath to generate the heat. I let it sit for a bit, and then I used my voltmeter to test the current that was coming off of my thermoelectric device, and I got a high of about 2.4 volts, which I'm pretty happy with because a lot of demos I was seeing were only around 1.5. So yeah, overall it was a really fun project to work on, and I'm super glad that I actually built the device because it's pretty cool what it can do.